Guys, are you ready for today's lesson? Let's do this with a simple curiosity in mind. What if the Earth has a large elliptical orbit?
What if Earth's orbit ventured as far from the Sun as Pluto and got as close to it as Venus? Would humans be able to survive such extreme changes in temperature? And if we could, what are the chances that Earth would follow this orbit safely through space without crashing into another planet? This is What If, and here's what would happen if the Earth had a large elliptical orbit. The Sun has a stronger gravitational pull on us than any other body in the solar system, but other planets are slightly pulling us towards themselves too. That, together with the Earth's velocity, makes the planet's orbit elliptical. The difference between the farthest and the closest point to the Sun in our orbit is less than 5 million kilometers. That's nothing compared to the overall distance of 150 million kilometers from us to the Sun. But what if that distance was much, much greater? The Earth orbits the Sun at just the right distance. Not so far away that we turn into an icy rock, and not so close that we burn to a crisp. We are in the Sun's habitable zone, where water can exist in liquid form. Even the slightest shift in the Earth's orbit would change that. The closer we got to the Sun, the more heat would hit the planet. As the heat became more extreme, all the ice on the planet would start to melt. Global sea levels would rise 70 meters. With little land left to absorb the scorching heat from the Sun, global temperatures would skyrocket. Our oceans would begin to evaporate. All this would leave us with a tremendous amount of carbon dioxide in the air, and little to no water left. The upcoming winter would be long and very cold. If there was any water left on Earth, it would freeze as we reached the minus 220 degree temperature of Pluto's orbit. If the Earth kept moving at the same speed it does today, it would take about 20 years to make a full orbit, from the hottest spot closest to the Sun to the coldest edge of our solar system. That is, if we didn't collide with any other planet on the way, which isn't all that unlikely. But it is likely that we'll be making this trip solo. The Moon might not be able to handle the pressure of this extreme orbital journey. Who knows, maybe we'd sail too close to Jupiter and become one of the moons of the gas giant.
Our God, the Father, the Almighty Creator, created the universe, the galaxies, the stars, and the planets with divine order and precision. All things were designed and well planned, mapped not by randomness or by accidents, but perfectly measured with His love for mankind. No miscalculations, no estimations, no trial and errors, no what-ifs. Everything is perfect. Last time, one of the techniques in drawing a circle was by the use of pushpin, a string, a pencil, and paper. Now, for your first challenge, how can you draw an ellipse or an oblong, a perfect oblong, using the same materials? Here are some other ways to draw an ellipse. Watch this video clip. Can you define now what is an ellipse based on what you did in Activity 3? What is that property of an ellipse that best defines it? An ellipse is the set of all points on a plane whose distance from two fixed points add up to a constant. The two fixed points are the foci of the ellipse, indicated as f sub 1 and f sub 2. The points that are farthest from the center are the vertices of the ellipse, indicated as v sub 1 and v sub 2. The vertices are the endpoints of the major axis. The points nearest to the center are the endpoints of the minor axis, indicated as w sub 1 and w sub 2. They are called the co-vertices. The position of the major and minor axis can interchange depending on where the ellipse lies, either along the x-axis or along the y-axis. The distance between a focus and the center will be denoted by c. The distance between a vertex and the center of the ellipse will be denoted by a. And the distance between an endpoint of the minor axis and the center of the ellipse will be denoted by b. The constant sum of the distances is the length of the major axis, which is equal to 2a. The lengths a, b, and c are related by the equation a squared equals b squared plus c squared. The major axis is longer than the minor axis. It follows that in an ellipse, a is always bigger than b. That is, a is greater than b. Think about this. What do you think will happen to the shape of the ellipse if we move the fixed points closer and closer to each other until the two fixed points becomes one while we are sketching? Take a look. Therefore, we can say that a circle is a special case of an ellipse. Whoa! It's from the definition of an ellipse where this standard form was taken. Just follow the steps in your module on how this equation was derived. That is quantity x minus h squared over a squared plus the quantity of y minus k squared over b squared equals 1. We know that at first glance, the graph of this ellipse with center hk lies along the x-axis, or it has a horizontal major axis because a is below the x variable. While the graph of this equation lies along the y-axis because a as the greater value than b is found below the y variable. What you really must remember about these forms is simple. Look for which has a bigger denominator and what variable is above it. Thus, it is where the major axis lies. What will happen to the standard equation if the center of an ellipse is at the origin? Yes, h and k values will be erased because the center has a 0, 0 coordinates. Let's have this exercise. Number 1. Using a graphing paper or a graphing notebook, graph the ellipse quantity x minus 4 squared over 36 plus quantity y minus 2 squared over 16 equals 1. Identify the coordinate of its center, find the values of your a, b, and c, how long is the major axis and minor axis, and where does the ellipse lies. Number 2. Transform the equation 3x squared plus 4y squared plus 6x minus 16y plus 7 equals 0 into the standard form of an ellipse. Number 3. Find the standard equation of the ellipse given this graph. Number 4. Two students are standing in a whispering gallery that is shaped like semi-elliptical arc. The height of the arc is 30 feet and the width is 100 feet. How far from the center of the room should whispering dishes be placed or the foci so that the two can whisper to each other? Here's a video clip to guide you what is a whispering gallery is and how does it works.
Imagine you're standing at one end of a large room and your friend is at the other end. You whisper something, barely audible to the person standing next to you. But your friend can clearly hear what you said. How amazing this would be, right? Is this possible? What do you think? Well, this magical thing is possible if the ceiling of the room is spherically shaped like an ellipse. This shape, which looks like a stretched circle, is what makes the whispering magic possible. If the ceiling of the room is elliptical in shape, technically semi-elliptical here, then there are two special points in the room where you and your friend can stand. If one of you whispers something, then all the sound waves get reflected from the elliptical ceiling towards the other person. So as the sound waves from one point get reflected and focused onto the other point, your friend can hear your whisper. This works the other way around as well. If your friend whispers something, you will be able to hear clearly as well. Based on this reflective property of ellipse, many rooms called whispering galleries have been constructed. Isn't this shape interesting? Each of these two special points of the ellipse is referred to as focus. And together, they're called the foci of the ellipse.
Another interesting application of the properties of an ellipse, like in a whispering gallery, is also found in the elliptical billiard table. What's the simulation? Game! That's all for now, guys. Thank you for your time and cooperation. I hope you learned something today. See you again in our next video where we explore the third member of the conic sections, the parabola. Stay safe, stay home, and stay productive. God bless. Bye-bye.